welcome, welcome everyone. Welcome to the numerical analysis for Galerkin ROM series. Today, it's a great pleasure to have Professor Yano from the University of Toronto give the talk. Professor Yano is going to talk about model reduction of parametrized aerodynamics problems, error estimation, adaptivity, and nonlinear approximations. I'm looking forward to this. It's a talk that showcases the power, I guess, of ROMs in challenging applications like compressible flows. That's quite a challenging application, and especially so we get to see some of the numerical analysis tools used to advance ROMs in this direction. So once again, a great pleasure. Masa, you can, the floor is all yours. Thank you.
Okay, well, thank you, Tryon, for the very nice introduction. And I want to also thank the organizers for putting together this very nice series and giving me an opportunity to give a talk here. So as Tryon said, in today's talk, I'm going to talk about our work on model reduction of parametrized aerodynamics problems with an emphasis on error estimation, adaptivity, and nonlinear approximations. So before I get started, I'd like to acknowledge that this is the work of my students who are listed here. And I also would like to acknowledge the financial support provided by the organizations listed below. Okay, so the motivation for our work is to provide rapid and reliable solution of parametrized aerodynamics problems in many query or real-time scenarios. So we are thinking of scenarios like parameter sweep, where we might want to change, say, angle of attack and Mach number and figure out how the drag, lift, or moment changes, or design and optimization, where we want to optimize the shape of the airfoil to maximize lift over drag, or uncertainty quantification, where we have a set of unknown input model parameters and then try to figure out its influence on the quantities of interest, or unsteady flow prediction of the flow like the one shown on the right. Now, as many of you probably know, one approach to address this type of problem is to use parametric ROMs. Now, parametric ROMs work on the principle of offline-online computational decomposition. So in the offline stage, we invoke the flow order model for a set of training parameter values to collect snapshots and then construct a reduced order model based on that. And then on online stage, we invoke the ROM for any parameter value, which typically is not in the training set, to predict the behavior of the system. So this process is pictorially shown in the middle. So this is my two-dimensional parameter domain. We compute the snapshot for the red dots, which are judiciously chosen. And then we invoke the ROM for, say, any of the blue dots in the online stage. Now, parametric ROMs have been around for quite some time, and technology is getting mature. But unlike simple textbook problems like parametrized Poisson's equation, aerodynamics flows exhibit a number of challenges, including severe nonlinearity, convection dominance, wide range of temporal and spatial scales, and limited regularity. Some of the features we see in aerodynamic flows are shown on the right figure. And all of these features produce a number of challenges, including expensive or inaccurate form. So this means that training of the ROM is going to be expensive because computing each snapshot is going to be expensive. It might take, say, order of hours or possibly days using parallel computers. And these challenges also introduce expensive or inaccurate ROMs. For example, if we are looking at transonic flow with moving shocks, we might have a very slow decay of Kolmogorov N width. And it also poses challenge in terms of certifying the ROM. So constructing the error estimate is going to be quite challenging for this type of aerodynamic flows. So with this in mind, the goal of our work is to enable model reduction for such challenging aerodynamics flow problems and be able to go from parameter to state to output in rapid, reliable, and automated manner. Now, when I say rapid, I mean providing orders of magnitude computational reduction in the online stage, but also ensuring that offline training is efficient. As I mentioned, computing each one of these snapshots is expensive, and offline training time becomes critical if we want to deploy this type of technique in a practical industrial setting. Second, we want our ROM to be reliable in the sense that we want to equip ROM with predictive and quantitative error estimate in online stage. And in the offline stage, we want to provide adaptive error control of all sources of error that exist in constructing a ROM. And finally, we want the entire process to be automated such that it requires minimum user intervention and problem-specific tuning. Now, we might argue that all of these challenges associated with rapid, reliable, and automated construction has been addressed using reduced basis method for simple parametrized Poisson's equations. So another way of casting our goal is to try to find answer to this question: can we bring to these challenging aerodynamics problems level of rapidness, reliability, and autonomy that reduced basis method achieves for simple textbook problems? Now, before we try to answer this question, you might notice that there's this notion of error control, which plays a key role throughout this talk. So I want to talk a little bit about model and error hierarchy before we dive into our work. So our goal is to approximate a solution to some truth partial differential equations, which is typically the Navier-Stokes equations. We discretize that to come up with a full order model, which might have tens of millions of degrees of freedom. We then come up with reduced basis space of order, say, 10 to 100 unknowns to create a reduced order model. And for nonlinear equation, it also requires additional what's called hyperreduction to enable rapid residual evaluation. So we have this hierarchy of models going from PDEs to hyper-reduced ROM. So if we want to use hyper-reduced ROM to create an accurate prediction of how aerodynamic system is going to perform, we need to really estimate the error and adaptively control the error associated with each one of these steps. So I would really like to think the error between PDE and hyper-reduced ROM is a sum of the errors coming from finite element approximation, reduced basis approximation, and hyperreduction. And our goal is to estimate and adaptively control each sources of these errors. Okay. Now let's start with the controlling the finite element error first. So for this, we're going to be using adaptive high order method, and in particularly the discontinuous Galerkin method. So DG method seeks solution in the piecewise polynomial space, like the one shown on the bottom right, and it's a space of discontinuous polynomials. Given such a space, we seek a solution, UH of mu, that satisfies the DG residual statement, which involves integration over elements as well as facets. And then given the solution, we evaluate the LS output, such as lift, drag, or moment associated with the aerodynamic body. Now, DG method has a number of attractive features. First, it provides stability for conservation laws, which is important for aerodynamic flows. Second, it works with unstructured meshes, which helps us treat complex geometries. And it provides high order accuracy by raising the polynomial degree and also facilitate adaptive mesh refinement. Now, these last 2 points are particularly important to control the error associated with our finite element approximations. I want to talk a little bit more about this. So our goal here is to estimate error in the DG output. We in particular care about quantifying the error in quantities like lift, drag, and moment. Now, to do this, we use what's called dual weighted residual method. So the idea here is that if we look at the dual solution characterizes the sensitivity of the output to perturbation from the perturbation in the equation. Now, in the context of finite element, perturbation comes from the residual. So by computing the dual solution and then weighing the residual with this dual solution, we can estimate the output of error in the quantity of interest, like lift and drag. We can also localize this statement to come up with elemental error indicator. So this process is shown pictorially in the bottom. So we compute the primal solution of the standard flow solution. We also compute the associated dual solution for the specific output. Combining this, we come up with the error indicator, like the one shown on the right. Now, if we say this error is too large, then what we are going to do is to refine the region that is contributing to large error. So we adaptively refine the mesh successively until user prescribed error tolerance is met. And this is how we control the error associated with a finite element solution. That's the first of the three pieces of the error we want to control. Now, I want to show you how well this class of method works. So we are going to be looking at this flow over an Onera M6 wing throughout this talk. And this is a subsonic turbulent flow, a Reynolds number of 1 million. Okay? And here I'm plotting the error in drag against the number of degrees of freedom using the finite element approximation. Now, using piecewise linear approximation, which results in a second order method, it requires about 33 million degrees of freedom if I use a sequence of uniformly refined meshes constructed following best practice. Now here I'm targeting 0.5% error level because I want to end up with a ROM that has about 1% error, and I'm allocating half of that to finite element and another half to model reduction. Okay? So this is what I get if I use second order method on best practice mesh. If we use adaptive mesh refinement, as we just described, we can do better. It requires about 5.5 million degrees of freedom, so factor of 6 reduction. But if you use high order approximation, we can do even better. So this is using quadratic, cubic, or quartic polynomials. And it only requires about 500,000 to 0.85 million degrees of freedom to achieve the same 0.5% error level. So key takeaway here is that adaptive high order methods are much more efficient than second order methods on these best practice meshes. And what this means in the context of more reduced order modeling is that using these methods can significantly reduce the offline training cost. Again, I want to emphasize that because solving this aerodynamic problem is quite expensive, if we are going to collect multiple snapshots, it's very important that we use efficient method. So we're going to try to build our reduced order model on top of this efficient high order DG method. So now let's talk about the model reduction for these high order methods. So our starting point, as usual, is to construct a reduced basis space. So here we could, for example, collect snapshots over the parameter space as pictorially shown on the right, apply something like proper orthogonal decomposition to construct a reduced basis space spanned by this orthogonal basis, which is illustrated on the bottom. And once you find such a reduced space, we can find the solution in that space by using Galerkin projection of the residual into this low-dimensional space. Now, one caveat here is that even though we have reduced the dimensionality of the problem, typically to order of, say, tens or hundreds, as opposed to millions for the finite element solution, we still have to evaluate this residual to perform Galerkin projection, and that requires evaluation of the residual for every single element in the mesh, which is going to be expensive. So we want to reduce the cost of this residual evaluation, and for this, we use hyperreduction. Now, there are many hyperreduction methods. We are going to be using the method based on the idea of reduced quadrature. So the idea here is to estimate the original finite element residual with this hyper-reduced residual that involves integration over a very small set of elements, which is shown pictorially on the bottom. So we're going to select a small subset of elements and then just try to estimate the residual. Now, obviously, the choice of the quadrature points and weights are critical for this method to work well. And we want quadrature rule that provides sparsity in the sense that it doesn't require evaluation of the residual in many elements, but also provides quantitative output error control. Again, I want to emphasize this notion of providing rigorous error control. We want to make sure that error in quantities of interest, like lift and drag, is controlled to user prescribed tolerance, even when we are using this reduced quadrature rule. Now, our approach to finding such a sparse quadrature rule is to optimize Castitzer's optimization problem and optimize this quadrature weight while constraining the error by imposing the condition related to dual-weighted residual. So it looks like this. So user set the tolerance delta, okay? And then we find the sparse weight subject to two constraints. One is non-negativity. All quadrature weights should be non-negative, and this is important for stability reason. And then we also impose residual matching condition. What this condition says is that we first introduce a set of training parameter set, xi EQP. And then we ensure that this reduced quadrature rule reproduces the exact residual to within the tolerance, which varies depending on the user prescribed tolerance, such that residual is reproduced at this set of training points. And by choosing training points that are sufficiently rich in the parameter space, we hope that error due to hyperreduction is controlled over the entire parameter domain. So this EQP method sparse weights like visualized on the right, but it also provides error control. We can prove under mild assumptions that the error in the output due to use of hyperreduction is controlled to the user prescribed tolerance delta. Third, it results in the solution of these linear constraints. So we can solve this using modified parallel non-negative least squares method. And finally, this method is quite versatile in the sense that this residual matching constraint can be replaced to hyper-reduced various form. This last set of constraints, we can replace it with other constraints such that we can reduce, for example, the form associated with the error estimate or unsteady problems and so on. And we're going to be leveraging this versatility later in the talk. So let's take a look at how this method works. So we revisit the same on-error M6 flow. This time flow is parametrized. So Mach number changes from 0.3 to 0.5, angle of attack from 0 degrees to 3 degrees. Reynolds number is still fixed at 1 million. We again allocate 0.5% for the flow order model, 0.5% for the ROM. And on the left in the table, I'm summarizing the result of solving this problem using adaptive DG method. Now, this is a result we've already seen at the beginning of the talk. I'm just summarizing it in the tabular form. Again, the key takeaway is that as the polynomial degree increases, number of degrees of freedom required goes down significantly. Number of elements also goes down, and computational time also goes down. Okay, so adaptive high-order DG method does enable efficient offline training compared to just using the standard linear method. Now let's take a look at how hyper-reduced ROM performs. So hyper-reduced ROM has about 12 degrees of freedom, and it ends up marking about 100 elements after hyper-reduction. Now, in terms of computational time, if we look at P1 approximation, it takes about 31 seconds on a single core of a computer. So it's a very healthy 10,000 speed up compared to just using the adaptive DG method with piecewise linear approximation. But notice that as the underlying polynomial degree increases, the computational time actually gets slower for the ROM. So somehow this method becomes increasingly less efficient for higher P, and this is unfortunate because high-order methods are more efficient in terms of the offline training time. And this is a result of basically, there are two causes for this. So first thing is that for higher order elements, at least for finite element-based formulation, we require more computation because it has more quadrature points. You can visually see that here. For P4 elements, it has a lot more quadrature points than P1 element. The second is that there are fewer number of elements to reduce. So these two meshes are one for the linear finite element, other for the P4 finite element. They both achieve about 0.5% error in drag. But you notice that P4 has much fewer elements than P1. This is great from the finite element computation point of view. But in the context of hyperreduction, what this means is that there's just much fewer opportunities for reduction. So the takeaway here is that this element-wise reduced quadrature formulation is not well suited for high-order DG method. And I want to point out that this limitation also applies to other algebraic or discrete hyperreduction methods like DEIM, because they still require the evaluation of residual for each discrete residual index. So how can we resolve this issue? So our approach to resolving this is to work with quadrature points instead of elements. So instead of just dividing the residual into elements and facets, we are going to further divide that to individual quadrature point level. That is shown pictorially on the right. So instead of just element and facet, we break it down into red dots for the elements and blue dots for facet. And then we think of DG residual as sum of the residual coming from these individual contributions. The rest of the process work exactly the same. We are going to still approximate the residual using hyper-reduced residual, which is the sum of the residual evaluated on a very small subset of quadrature points, like the one shown in the figure. And we find this using, again, the empirical quadrature procedure. So user prescribe the tolerance delta. We try to minimize the number of non-zero points subject to non-negativity constraint and residual matching condition, which again says that over a set of training points over the parameter domain, our reduced quadrature rule have to match the exact residual to within user prescribed error tolerance. Now let's take a look at how this method works. We are looking at exactly the same Onera M6 problem, subsonic turbulent flow. Adaptive DG result is what I have shown you already. One thing I have added is the number of quadrature points. You notice that it has basically tens of millions to millions of quadrature points. We've already seen the result of applying hyperreduction based on element-wise quadrature to this method. We end up choosing about 100 elements, but basically the computational time increases as the underlying polynomial degree increases. With point-wise formulation, though, we end up choosing about the same number of points and the computational time remains the same. So with this point-wise formulation, takeaway is that we achieve P-independent online cost. And in addition, we provide about a factor of 70,000 computational speed up. So this method is, in general, more efficient than element-based version, and in particular, when we are looking at higher order discretizations. Now, one thing you might be wondering is finding, say, a subset of 200 quadrature points out of tens of millions of points, is that going to be a very expensive problem? So I want to recall that this point-wise EQP requires the solution of very large sparse quadrature point identification problem with this residual matching condition. The number of quadrature points, again, is in tens of millions. And in terms of computational time, yes, it's not really cheap. So this is a cumulative CPU time or using 80 to 160 cores. But compared to the DG solve time, it is still a small fraction of a single DG solve time. I want to emphasize that this is for single snapshot, not for multiple snapshots. So hyperreduction time is still cheaper than computing single snapshot. It's about 30 to 70% of a single DG solve. And this is really thanks to this non-negative least square solver that parallelizes well. Okay. Now, I want to also show the application of this to slightly simpler problem, arguably. So this is just a 2D problem with geometry deformation. So we have basically 8 points that can be moved around using freeform deformation. And we want to predict the drag for different geometries. We again divide the overall error into 0.5% for form and 0.5% for ROM. Now, when we solve this problem using adaptive DG method, it works very, very well. For example, piecewise cubic approximation, which is fourth order method, it only requires about 11,000 degrees of freedom and 270 elements. Okay? So that's very efficient. But what that also means that when you work with element-based reduction, there's really not much opportunities for reduction, and we can only achieve about factor of 3 to 4 speed up. But with point-wise based version, we achieve much better computational speed up of order of 300, 400, which is a much healthier number. And if you're going to take basically one picture away from this talk that compares element-based and point-wise based formulation, it's really this one. With element-based formulation, it works well for low-order approximation, where the number of elements is quite large. But as the polynomial degree increases, it loses efficiency because there are just not that many elements to reduce, and because computing residual on each element gets very expensive. With point-based formulation, we basically get P-independent performance, And it also, in general, achieves much more significant reduction than element-based formulation. Okay. So summarizing this part of the talk, we saw that element-wise reduced quadrature or any algebraic or discrete hyperreduction method can be inefficient when applied to these high-order methods. But point-wise formulation can resolve this issue. And we can really think of this reduced basis, reduced quadrature formulation as an empirical high-order method for these parametrized problems. So DG method or any finite element method works with piecewise polynomial basis and piecewise Gauss-like quadrature. Reduced basis, reduced quadrature formulation work with empirical basis, which might come from, say, POD, and empirical quadrature, which comes from EQP. Now, there is one caveat, though, actually two caveats. One is that particular pointwise formulation I presented is limited to DG schemes without lifting operator. We have to have a residual form that can be decomposed into individual quadrature points. And those schemes with lifting operator that couples degrees of freedom within elements doesn't permit this decomposition. Second is that unfortunately, there is no provable or energy or entropy stability for the current formulation. We do add entropy constraints at the set of training points, but in general, that does not mean that we have energy or entropy stability for all of the parameter values in the trains parameter set. Okay. So that's basically our baseline hyper-reduced ROM. So now I'd like to talk about error estimation and how to control the error associated with these ROMs. So we have twofold goal. First is to estimate the output error. So by this, what I mean is the error between the full order model solution coming from DG and our reduced model approximation. And we want to do this in an online efficient manner in predictive setting. So it has to be very fast evaluate, and it should work for any parameter value, even if that's not in the training set. And second, we want to control the error coming from finite element, reduced basis, and reduced quadrature in an automated manner. So let's try to answer the first part first. Now, we are going to be using the dual weighted residual method again, just like we did for the finite element formulation. The key difference is that we are going to also apply model order reduction to the evaluation of this dual weighted residual. So first, we introduce this dual space, which is spanned by dual solutions like the one shown in the figure. We then solve the dual problem in this reduced dual space by using Galerkin projection of the dual problem. And then we evaluate the dual weighted residual using this approximation to the dual problem as a surrogate for the true dual. So this provides a reduced basis approximation of the DWR. And yes, the dual solution is approximated in the low dimensional space, but one limitation again is that it requires evaluation of this high dimensional residual for Galerkin projection. But we already know how to solve this problem. We can also hyper-reduce this dual problem. So we again use the empirical quadrature procedure to hyper-reduce the dual problem and residual evaluation for DWR. And we replace those residual matching condition or the accuracy constraints with those appropriate for the dual problem, such that we can control the error due to hyper-reduction in the solution of the dual problem. So again, the process is pictorially shown in the bottom. Primal solution, dual solution, hyper-reduction, and that provides an online efficient error estimate. So with this, we can provide quote certified prediction, where we can go from parameter to state to output, and also equip that output with an error estimate for any parameter value, which is in general different from training parameter value. The limitation here is that it's not an error bound. So reduced basis method for textbook problems provide a rigorous bound. To my knowledge, or at least we cannot provide such a rigorous bound for this class of nonlinear compressible flow problems. But in any event, once we have such an error estimate, we can actually enable automatic training of finite element, reduced basis, and reduced quadrature by using a modified version of the classical greedy method. So the way the method works is that we introduce a set of very large training set, and then we basically evaluate the ROM at all of these blue dots and associated error estimate to find the point that is least well approximated. Once we find such a point, we solve the full order model at that point, and we are going to perform adaptive mesh refinement as necessary to make sure that our snapshot is accurate. We then update the primal and dual reduced spaces using that adaptively computed snapshot, and then update the reduced quadrature weights. And then this process repeats. So we're going to look for the next point where the error is maximized, update the ROM, find the next point, update the ROM, and so on, until user prescribed error tolerance is met for all of the blue points. And the idea is that as long as you select sufficiently rich set of blue points, it's going to cover the entire parameter domain. Let's take a look at how this method works. So we again revisit the same Onera M6 problem, and I use this greedy algorithm starting with a very, very coarse mesh. So the algorithm terminates after 9 iterations in this case. And in that process, it's going to basically perform adaptive mesh refinement every time it computes a snapshot. So the final mesh has about 1.1 million degrees of freedom, and this mesh achieves less than 0.5% error in drag compared to the initial mesh that had 114% error. Now, in terms of the ROM that's been constructed, we end up with a ROM with just 9 modes, and hyper-reduced ROM reduced the number of quadrature points from 6.3 million to just 153 for flow computation and 177 for the dual problem. This is basically the convergence behavior we observe over the set of training set. Now you might be wondering, okay, does this still work well for a set of test points which are completely independent of the training points? So I test this over the set of 5 test points and look at the worst case scenario. And for the worst case parameter value, first of all, the blue line, which is the error, we see that error does go down over the test set. But perhaps even more encouraging is the orange line. So orange line is the error estimate, which is again using a completely predictive setting because test set and training set are unrelated to each other. And we see that error estimate tracks the true error really well, even though this is a nonlinear turbulent flow. So it works very well. Now, in terms of speed up, we observe about a factor of 21,000 speed up in wall clock time. And this involves both the computation of the flow solution and the output, and also the dual problem for the effective error estimate. Okay? So that's a factor of about 21,000 speed up. So this method works quite well. And the reason it works well is because, again, I want to kind of review this approximation hierarchy that we introduced in the beginning. We said the error between PD and hyper-reduced output is a sum of the error coming from finite element, reduced spaces, and reduced quadrature. Now, we have devised a method to estimate the error due to finite element and this ROM approximation based on DWR. One of them is just based on standard finite element DWR. Other one is its reduced model reduced approximation of the DWR. And we have a means of controlling these errors using AMR, greedy algorithm, and empirical quadrature procedure. So with this, we can enable automated construction in the sense that we provide problem description in terms of the geometry of the problem and the parametric range, and then specify the tolerance. I want my ROM to be accurate to within 1%. The rest of it, algorithm compute everything automatically using this automated loop to construct this certified ROM. Now, this class of method can be extended to other problems as well. One such extension is higher dimensional problem. So we want to enable model reduction of moderate to higher dimensional problems. Example of such a problem is uncertainty quantifications of Rand's turbulence model. So in this case, we'll be looking at 7 parameters of the Spalat-Almaras turbulence model. And this is an empirical model, and we treat parameters as uncertain. It has certain distribution, like the one shown in the figure in the middle. And then we want to understand how variability in this turbulence parameter is going to influence the quantity of interest, which is drag in this case. Okay? So this is a 7-dimensional uncertainty quantification problem involving subsonic turbulent flow. Now, one key thing is that in order to provide rigorous uncertainty quantification, we cannot conflate the uncertainty coming from model parameter and discretization error. So we have to provide a tight control of the discretization error to enable reliable UQ, and we will be shooting for basically 1% error level, 0.25% for finite element, another 0.5% for reduced basis for this problem. Now, there is a challenge in applying the algorithm that we just talked about for this high dimensional problem. One is that in order to ensure model accuracy for these high dimensional problems, we need a lot of training points such that we can cover this high dimensional space well. But in order to make sure that offline training cost is not so large, we want training set to be small. So there's these two conflicting requirements. Now, our approach to try to address this conflicting requirement is to combine three ingredients. So first one we've already talked about, which is online efficient error estimate. As I mentioned, ROM provides a speed up in the order of 1,000, so we can easily use a training set in the order of 1,000 points in high dimensional space. But this alone is not enough. So we are also going to perform adaptive refinement of the training set and the adaptive enrichment of the EQP training points based on the behavior of the error. I'm going to skip the details in interest of time, but I just want to show you the result that this class of moderate dimensional UQ problem can be tackled using reduced order model. So we again use a greedy algorithm. This time it terminates after 12 iterations. We're actually collecting 2 snapshots per greedy iteration in this case. And then we basically terminate after 12 iterations. Our mesh again gets refined. Initial mesh is a very coarse mesh, had about 23% error. Final mesh has less than 0.25% error. Now, in terms of the ROM being generated, it ends up with 24 degrees of freedom. And then the quadrature point reduces from around 100,000 to about 500 for flow computations and 200 for the dual problem computation. And this is the greedy error convergence behavior over a fairly large training set. Now, you might be wondering, how does it work over test set? So we again, this time choose 20 randomly chosen test set. And we observe that first of all, the true error in blue curve does go down. But also the error estimate, except for the first few points, is actually quite accurate, even again in this predictive regime in high dimensional space. Now, in terms of training cost, it is not cheap. It requires equivalent of about 60 CFD solves, 20% of which comes from just computing these 12 snapshots, but there are also additional costs associated with hyperreduction and sampling. And but if we pay this cost, we can provide an online speed up in the order of 300, and this again involves computation of both output and error estimate. Now, one limitation here is that we are assuming that intrinsic dimension of the problem is small, in the sense that the problem is reducible, right? So even though the extrinsic dimension, you might have many parameters, there is a low dimensional space within that can be approximated well. So that's an assumption we're making. So we've talked about extension to higher dimensional problems. It also extends to time-dependent problems as well. So for example, which is a separated flow over Nakadabdo 12, equations compressible Navier-Stokes. We have angle of attack at high angle of attack of 20 degrees. Mach number is fixed, but Reynolds number varies from 300 and 600. And we are interested in a time averaged drag. Now, everything we have talked about in this talk readily extends to this class of high dimensional problems. So we have a reduced basis space that approximates both the parametric and temporal manifold. We have this quadrature point that can be obtained for these time-dependent problems. And finally, error estimation and control still works by appealing to space-time formulation and unstudied adjoint, like the one shown on the bottom right. Let's take a look at how does this work. So again, we do greedy for this unstudied problem. We end up sampling just at 3 parameter points for this 1 parameter problem. In that process, our mesh also gets refined. You can see that there's lots of refinement in the wake region. And our final ROM has 42 degrees of freedom and about 1,200 quadrature points for the primal problem and 800 for the dual problem. And we see this rapid convergence over the training set. Now, over the test set, we again see a pretty rapid convergence. You might notice that this error estimate shown in the orange curve is not quite as good as the ones we have been getting for steady state problem, but nevertheless, it still provides reasonably effective error estimate. Now, in terms of computational speed up, it's in order of 300. If we want to just compute the solution and the output. If we want to also equip that with error estimate, we have to solve that unsteady adjoint problem, which is not exactly cheap. So speed up goes down to about a factor of 200. So that's an extension to unsteady problems. And of course, we can also probe the time instantaneous response of, say, drag and lift. Now, one limitation, though, is that we are still limited to fairly low Reynolds number and also short time integration. If you look at very high Reynolds number flows, you get into an issue with the reducibility. Now, we have also looked at the application of this class of method to other problems, like using in the context of data assimilation. We have devised multi-fidelity ensemble Kalman filter and on-the-fly hyperreduction technique. And this can achieve factor of 8 word clock reduction at comparable accuracy. And we have also used in the context of ROM accelerated PD constraint optimization, where we use error-informed trust region and on-the-fly hyperreduction and achieve about 40% word clock time reduction. For both of these, we are starting with scratch, so there's no offline training. So these are genuine speed up compared to basically non-reduced methods. Now, the last thing I want to talk about is the extension of the method for transonic flows. You might have noticed that all of the problems I have shown today so far have been subsonic flows, which doesn't have shocks. So I want to talk about its extension transonic flows. And to do that, I want to first illustrate the challenge. So here I'm looking at single parameter problem, subsonic flow with parametric range of 0.2 to 0.6 Mach number, and transonic flow with a Mach number varying from 0.78 to 0.8. You might notice that Mach number range is much wider for subsonic flow than transonic flow. Okay? Now I compute 10 snapshots equispaced over this parameter range and apply POD and construct a ROM following the procedure that I have described. And here is the result I get. For subsonic flow, we see the lift error shown here, and we observe a very rapid convergence, the one very similar to the ones we have been seeing for all other subsonic flows. But notice that for transonic flow, error doesn't really go down even after using 10 basis functions. Okay? So we observe a very slow error convergence. And the reason for this is quite well understood. And we can illustrate this by just looking at ROM construct based on 2 snapshots. So let's say we compute one snapshot at the Mach number of 0.78 and the other one at Mach number of 0.8. You notice that shock sits further back for this higher Mach number solution. Now, we're going to try to predict the solution at Mach number of 0.79. Now, the correct shock basically lies in between these 2 shocks. But of course, if we are considering linear combination of these 2 snapshots, we can't really represent this type of translation. So the best we can do is to represent the shock that sits in the middle with this 2-step shock shown on the figure on the right. Okay? But you can probably guess that the lift or drag estimate based on this type of 2-step shock structure is not going to be very accurate. And we can, so this is an illustration of the challenge. We can also formalize that mathematically as well in terms of a Kohn model of n width. So we can think about basically the maximum error associated with best fit error estimate, best fit L1 error, I'm sorry. And then we consider a bunch of different spaces. And you can show that even using, if you consider linear spaces, even using the best space, error only converges as 1 over n. So this is using the best linear space. So the key takeaway here is that if we want to provide rapid convergence for this type of problem with moving discontinuity, we must consider nonlinear approximations. So one way to construct such a nonlinear approximation is to consider transformed snapshots. Now, this class of method has been used by many people who are listed here. And the idea goes as follows. So we first introduce parametrized transformation. I'm going to use mu to denote the parameter of the transformation. Okay? And then we compute shock-aligned transport snapshots. So if you could focus on the figure on the left, this is the actual solution computed in the physical space. So as the Mach number increases, you can see that shock moves back. Again, going back. Mach number increases, shock moves back. Okay. What we are going to do is to apply transformation to each one of these snapshots such that shock doesn't move much at all. So on the right is a result of applying this transformation, each one of which is parameterized. Okay, so we apply different parameter transformation for each parameter value. And if you focus on the figure on the right, you notice that shock hardly moves in this transformed space. Now, once you construct such a transformed snapshot with roughly aligned shocks, we can create a reduced basis space using this transformed snapshot and then approximate the solution in this transformed space and then transform it back to the physical space. Okay? So that is basically the way we construct nonlinear approximation space. It's nonlinear because we are applying this transformation to the snapshots. Now, I'm going to talk just a little bit more about how this works in practice. So one of the key ingredients is this parametrized transformation. And of course, we have to preserve the boundary shape. When we apply the transformation to the domain, the shape of the domain has to be preserved. The airfoil should still be an airfoil, the same airfoil. To do this, we borrow the idea discussed in Tommaso's paper. So we combine the transfinite map and C2 parameterized FFT map. So transfinite maps from the square domain to subset of the domain, like the region above the airfoil where shock might be located. And the FFD map basically just transforms the points inside this unit square domain. And by considering the composition of this map, we can basically enable transformation while preserving boundary. So we take a subset of the domain where shock is going to be, transform it to a square domain, perturb the domain using FFT, and then map it back to the airfoil shape. So that's how we construct these parametrized maps. We also need a way of identifying the shock location, okay, to identify appropriate map. So we start with a solution like one shown on the left and compute the dilation-based shock indicator, which measures the divergence of the velocity, which highlight the region where shock is located. And then we further reduce this to just simple statistics by introducing these sigma point, which are the orange point that characterizes the location of the shock. I should emphasize that our current formulation, this statistics is very simple, and it is specialized for this type of simple transonic shocks. Okay? But once we can summarize the location of the shock using this set of points, we can find the optimal transformation that minimizes the distance between these sigma points for the reference configuration and the current configuration of the interest. So we solve an optimization problem for each snapshot in the offline stage, which minimizes this mismatch of the two shock locations. Now in the online stage, we are typically given parameter values that are different from the snapshot parameter values. So we have to approximate the correct transformation. And for that, we just use Gaussian process. We use Gaussian process because it works with unstructured data set, but also because it is robust against noise. And as you might have figured, the shock location identification is not perfect. It can be noisy, and it has, in general, the error in the order of the mesh spacing used for the computation. So we want to denoise that by using Gaussian process. Let's take a look at how the method works. So again, we revisit the same NACA 0012 problem that we had been looking at, transonic flow Mach number changing from 0.78 to 0.8. We've already seen the linear ROM doesn't work. This is the result obtained for the greedy algorithm, and we are looking at drag now, and we see that it shows very slow convergence. With nonlinear ROM, we see much more rapid convergence, and we hit the target error using just 7 basis functions. This also significantly reduced the number of hyper-reduced quadrature points to just 188. And of course, error is smaller, less than 0.5%. and we achieve a healthy computational speedup in the order of 38,000. So this nonlinear formulation provides in the online stage reduced ROM size and reduced quadrature size. But it also has a benefit in the offline stage. As I mentioned again, computing each snapshot is expensive, so we want to control the offline training cost as well. Well, with this nonlinear formulation, it does reduce the number of snapshots required to just 7 for this particular problem. But in addition, it avoids the need to construct a universal mesh that works for all different locations of the shock, because in the transformed domain, shock basically sits in the same location. So number of form degrees of freedom is also smaller to achieve the same error level. Now, we can also equip this ROM with an error estimate using exactly the same technique we have talked about, dual weighted residual and hyper-reduced DWR. And here's the result I get. So error estimate is not perfect. If you compare to the true error, it follows it pretty well, not perfect. There is a severe underestimation for the first point, but it does provide a reasonable quantitative error estimate. Okay? And I want to emphasize again that this is for the test set, which is completely independent of the training set. So this is in a predictive setting. So that is our application to transonic flows. So in summary, in this talk, we talked about goal-oriented ROMs based on adaptive high-order DG, point reduced space, reduced quadrature, and DWR that provides quantitative and automated output error control. Again, we decompose the error into finite element, reduced spaces, and hyperreduction, and we try to estimate error coming from each one of these sources and control the error in an automated manner. And we also showed its applications to parameter sweep, uncertainty quantification, unsteady flow, and so on. So I think we are making steps towards bringing to aerodynamics the level of rapidness, reliability, and autonomy that reduced spaces method achieves for textbook Poisson problem, but there are still many challenges. So it works with compressible flows, even with the one with shocks, but at least our formulation is limited for simple shock geometries. It works with turbulent flows, but with Rand's model. It works with unsteady flows, but at low Reynolds number and for short-time integration. We have hyperreduction, but there's no stability guarantee. There is nice online efficient error estimate, but unfortunately, it's not a bound. And finally, we can apply it to higher dimensional problems, but it has to have low intrinsic dimension. So I think there are still many challenges that we can look at and try to overcome. But again, this talk tries to basically summarize the work that we've been doing in our group to bring the ROM to these more complex aerodynamic flows. If you are interested in our work, here's the kind of list of publications that are most closely related to the work I presented here in this talk. So I want to thank everybody for your attention, and I can take any questions that you might have.
Very nice. Very nice. Thank you. Thank you, Masa, for an excellent talk. Now, if there are any questions, you can unmute yourself or just raise your hand and ask. I mean, I don't see any hands. I can start with a question. Okay, Matt, do you want to ask a question?
Yeah, I have a question. Can you talk about the generality of the excuse me, the generality of the approach that you mentioned for aligning the shocks when you have more complex geometries, not necessarily complex shocks?
Yeah, so our current formulation is quite limited. We are really just targeting these simple transonic shocks that are, it can be described in basically a simple horizontal motion and maybe a little bit of curvature. Okay, so we are not looking at, for example, geometry over things like supersonic, cylinder or something like that. And the reason that we have limited abilities is, first of all, the way we construct this map, we basically identify a small region where we apply the transformation, and that is typically attached to, for example, airfoil or wing. So it has to be a fairly small region. So that's one limitation, but the other one is the way we detect the location of the shock. Again, we are reducing that to just simple these 5 points in the current formulation, and then solving the matching problem. So compared to actually doing the full field matching, we are losing a lot of information. So that is the limitation of the current method. But one of the reasons that we avoid this field matching problem is because that requires the kind of projection of the two unstructured meshes, which is a quite challenging problem, especially if you want to parallelize it well. In the serial setting, it works fine, but in parallel, it becomes a very difficult problem to solve. So we are reducing that to this simple statistics. So those are the the kind of limitations compared to kind of method that you're developing. That's definitely one of the big limitations. Of course, the other one is that our shock is not sharp, right? There's a thickness to our shock, so that's another issue that we have as well. I'm not sure if I answered your question completely.
Yeah, no, you did. I just have a quick follow-up to it though. Is that so? I guess the application I was thinking about is your own narrowing, where you've got a shock that goes all the way to the boundary of the where the is you think that would be an issue, or is that fine with the approach to the constructing dynamics?
So we haven't tried on narrowing yet. That's basically our next step. That's the next thing we want to try. So in 3D, I think it's a little bit hard to say. So I think so basically the kind of fuselage wing junction, that part I think is okay, because you can kind of define a box over the entire thing, and you can move the things around using FFT. That part is okay. The wingtip might be a little bit more challenging, depending on exactly how the shock looks like on the wingtip. But these are things that we still need to work out. So I can't really provide a concrete answer right now. I think the other concern is that obviously in the 3D case, the shock is a two-dimensional feature. We'll try to approximate that using 7 points, for example, using this formulation, but does that provide sufficient information? I'm guessing the answer is no. We probably need more detailed information of the actual structure of the shock, because shock is not perfect, straight, right? It's halved. So, but yeah, we are trying to figure these things out as we go. And I think the other thing I might point out is that we are not really looking for perfect alignment here. We are just trying to basically come up with a closer alignment. I think that's really what we are shooting for. So it doesn't really address this issue of conomodal width at fundamental level. What we are trying to do is to kind of reduce that issue. So I think it's a little bit different. Like your approach addresses that challenge completely because you have a perfect alignment, but we don't quite have that.
Yeah, great. Thanks. Great talk as always.
Very nice. Thank you, Matt. Anybody else? Oh, yes. So I can see a raised hand. So Tomas, yes.
Hello. Thank you for this so kind talk. I have a question concerning the application to turbulence models. You mentioned that it is only applied to RANS methods. So I have the question, why is there this intrinsic difficulty for LES methods, or what is the reason?
Yeah, thank you for the question. So we are looking at RANS because so if we look at LES, we are looking at obviously time-dependent simulations, right? And we are going to get a fairly wide range of scales because you are at least resolving some part of that turbulence scale, depending on exactly where the filter cutoff is. And that is going to require basically dimension of the reduced basis space required to resolve that, those eddies to that scale is going to be quite a bit higher. In the RANS model, all of those eddies are completely modeled. So as far as approximating the solution goes, it's a much simpler problem because we are not resolving any of those eddies. I think Tryon in the first talk of this series showed that if you have like wall-bounded flows, the number of modes required to actually resolve that is basically really, really high, and with the Reynolds number, obviously it's going to get even higher. So we are not really we recognize it's a very important challenge, obviously, because RANs have severe limitations, but we are not really tackling that challenge right now. Partially because for many of the industrial scale aerodynamic flows, RANs are still very frequently used because it's much cheaper than LES at the full order model level as well. So that's the class of problem we are trying to tackle. But yeah, we very much recognize that challenge for the LES and its importance. Yeah.
Okay.
Does that answer your question?
Perfectly. Thank you.
Thanks, Thomas. Thanks, Thomas. So I saw Matt. So you have another raised hand?
Yeah, sorry, I got just one quick question, and then I got to run to a dissertation. So you mentioned that you have you solve your linear program using a non-negative squares method. Is it obvious how to reduce an LP to a non-negative squares problem, or can you talk about that for a second?
Okay, yeah. So that's a great question. So it works only because of the way we solve the NNLS method. So we are solving NNLS using greedy method, right? So you basically introduce new points in a successive manner, and we basically stop as soon as we meet all the constraints of the method. So it's not like we are actually I don't think there's formal, as far as I know, there's no formal relationship between NNLS and the original L1 minimization problem. But what we are doing is to use the fact that we solve the problem in a greedy manner, and the fact that that process introduces this sparse set of solutions. We are using that, I guess, in a sense, heuristically, such that we end up with a sparse set of points. Does that answer your question?
Yes, it does. Thank you very much.
Okay.
Thanks, Matt.
Perfect.
Thank you. Tommaso. Yes, go ahead.
Thanks, Tryon, and thanks, Masa, for the very nice talk. I have, plenty of questions, but I have like two curiosity if you can ask. So curiosity one, so concerning to sampling, you certainly have, a significant overhead related to the greedy method and so on. So I'm wondering how different your sampling in the end is from uniform sampling. So say that you just do a uniform sampling. Is it really that much worse?
Yes. Okay. So that's a great question. I don't know. So I guess that's very much problem dependent, because we can certainly, I think, construct problems where uniform sampling performs well by scaling parameters in a certain way. I think that, I guess that's the mathematical answer to the question. But in practice, short answer is I don't know, but I can. Yeah, I don't know. I guess you're thinking uniform in a form of like grid or just completely random sampling. Is that kind of what you're thinking here?
Yeah. It's just a curiosity for your test cases, because what I observed is that from whenever you have like viscosity of Reynolds, then it's better to have some kind of log uniform type of stuff. And, but I was wondering if you have tried.
No, so yeah, we haven't really done much quantitative comparison. We use POD as well, right, to kind of isolate certain aspect of the problem when we develop things. But I think the final runs we typically use greedy. So, but that's a great question, because obviously greedy method introduces a number of complexities, right? Starting with just having an error estimate and basically the entire structure. So that's a great question. Do you have so I guess your sense is that it might not make that much difference for the classes of problems that you typically solve?
I don't know.
Okay, all right.
No, I was really have no idea about the answer. So no.
Right. Okay. Any other question, Tommaso?
Oh yeah, so one curiosity is, do you have, like, when you use non-negatively squared, do you have an off-the-shelf algorithm, or is yours that you implemented the parallel version of NNS?
Yeah, it's in-house implementation, and we had to actually make a number of changes to make it work well. You tend to get into some of the kind of issues associated with numerical stability for these like really large problems. So we had to make a number of changes to kind of the standard algorithm. We are working on writing a paper on that, so it should be hopefully be in the public domain pretty soon. But yeah.
Thanks. No, I think that would be a really, really good contribution, because I mean, at least in our group, we do have issues with that, saying that, you know, if you use the standard non-negatively squared from Python, or if the problem gets big, then we have, I mean, at least us, we are experiencing issues. But yeah.
Okay. Is the Python version, is it parallel or not parallel?
No.
So,
I don't know that.
Okay. Right. So, because for large problems, I don't think it would even fit in like one machine, right? It has to be distributed, right? So, okay.
Yeah, but thanks.
Thank you, Tommaso. Anybody else? Any other questions for Masa? I can ask a question. I've been meaning to ask this. So first of all, I was impressed. I mean, I thought that the error estimators, the a posteriori error estimators, work very well for these challenging problems. I mean, you really got, like, you know, good alignment. Even when you said, oh, they don't look great, to me they look great. So that was impressive. Now the question I have is, so on slide 23, I think that you mentioned that there is no such, so there is theory for you know, for simple textbook type of problems. So right, but my question is, and the idea was that maybe there is no such, there are no error bounds, there's no provable there are no provable error bounds for the nonlinear challenging cases. And my question was, of course, I mean, makes sense, I understand, but I was thinking, so what is the main challenge? Is it going to the nonlinear case plus predictive? What exactly prevents one from extending what's proved at the basic Poisson level to, you know, Navier-Stokes and compressible Euler?
Okay, so I think that's a great question. And when I say, you know, there is no way, I guess what I mean is that at least I don't know the way. I guess that's all I meant. I'm not saying it's impossible or something like that, right? But I think one thing I can say is that many of these error bounds actually draws inspiration from the finite element counterpart. And to my knowledge, even in just a finite element setting, there is no error bounds for the nonlinear compressible flows. And the bounding techniques, and there are ones for Poisson's equation, or the, you know, the linear elasticity problems and so on. And my understanding is, so two things. One is linearity, which might be kind of obvious, but other one, which arguably is even more important, is I think the convexity of the problem. So it needs to be convex, because many of these bounding techniques are based on kind of the primal dual type principles. You try to come up with kind of an estimate of the energy from above and below by looking at the dual problems. And that is what provides a rigorous bound. And, you know, things like Poisson's equation, the linear elasticity, and even like even if you have I guess hyperelasticity problems, I think in principle you have such a convex structure, but for fluid problems we don't, right? So that, I think, might be actually bigger issue than just nonlinearity. It's really the lack of convexity. So that's, I guess I should say, it's my opinion, right? I'm not saying that that's true or not, but yeah.
Okay, so just a quick follow-up. So this is great. I agree with you. I mean, so if it doesn't work at the finite element level, I mean, so that's, but are you saying, are you implying that if it works at the finite element level, that it's conceivable to try to extend this to the RBM level? Would that be fair or not?
I guess it depends on exactly how it looks like at the finite element level. So it's a little bit hard to say, but right. It's like, for example, going back to this problem with this convex structure, if it has that primal dual type structure, then you can come up with just reduced approximation of the dual problem as well, right? So then it works. But I don't. It's kind of hard for me to imagine how it looks like for this type of plot if it's possible. But right. So yeah, I guess I can't quite answer the question, but yeah.
Fair enough. Fair enough. This was an excellent, excellent answer to my question. Thank you, Masa. Are there any other questions for Masa? So Masa also, agreed to. So he was glad to answer any questions you might have if you contact him directly about any of the slides and papers.
I asked a quick question.
Sure.
Quick question is, what tool did you use? Did you use some free form and then you added the other aspects of it, or what did you use? Phoenix or MFM, or you have your own developer?
Okay, so everything I present, this is all in-house code. So we didn't really use finite element library. So our DG solver is our own implementation of the DG solver. We looked at different packages, but one of the things we couldn't quite figure out is that when we do this mesh refinement, one of the important features is to be able to perform anisotropic mesh refinement. So not just refine elements in a uniform manner, but for this type of aerodynamic flows, we need these anisotropic refinement capabilities. And to my knowledge, there are many excellent finite element packages out there, but at least at the time we started developing the code, we couldn't find one that supported this type of anisotropic refinement. So we ended up kind of building our own thing. But that might not be true anymore. Maybe there are some package that supports this type of anisotropic refinement. Yeah.
All right. Thank you very much.
Any other questions for Masa? Well, if not, then Masa, thank you again for a wonderful talk as always. This was excellent. Thank you. I learned a lot. Thank you so much. And for the rest, so we'll have the next NAGRAMS seminar will be next Tuesday. Professor Volker John will give a talk, and we're looking forward to having you join us then. Thank you, Masa, again, and have a wonderful day.
Yeah, thank you everybody for coming. And if you have any questions, please feel free to email me. So thank you again.